Okay, hello everybody, and welcome to the Spark and AI Summit 2020. I hope you guys have been having a great time from the comforts of your own homes or wherever you are this year. You are at this talk, Sepsis Prediction, a Unified Workflow from EMR Data to ML Model Design. If you are not here for this talk, you're in the wrong room, but feel free to hang around. It might be interesting. So my name is Sela Benheim. I work for Prominence Advisors. This is us, and these are all the wonderful organizations, healthcare organizations that we work with. And in our work with these organizations, our job is to help them do more with their data. And ultimately, our mission is to make healthcare smarter. And today, the purpose of my speech is to show how, with Databricks and this concept of unified analytics, we make our jobs easier, and we help the organizations that we work for. So the topic that we're going over today is sepsis. And I'm not going to read through these, but the takeaway of this slide is that sepsis is a serious illness. It's basically, if you're not familiar, it's just a very severe infection. It's a major cause of death and in hospitals. And so anything that we can do to help improve our response to sepsis or reduce mortalities around sepsis is a very positive change for the healthcare industry. So with that context, I'm going to jump right in. Today, we are going to be taking a data journey. We're going to start by extracting data out of our EMR. We're going to prep that data with Spark SQL, and then we're going to explore the data and work towards building a sepsis prediction model with PySpark. The purpose of this journey is really, again, you probably, if you've been around the Databricks ecosystem, you've heard this term unified analytics, and the proposal that with unified analytics, you can bring together your data engineering and data science. Well, what does that mean? How does that actually make you and your team more efficient? How does that allow you to achieve your objectives? So that's what we're going to try to show. But in fact, we're going to change up the agenda a little bit. I've got something a little bit even better for you. We're going to skip the extraction out of the EMR part, and I'm going to quickly swap in delta merge for change data capture based on recent work that we've done. So let's dive in. We're going to start with that one. So what is this change data capture, and why is this important for healthcare organizations? So you no doubt, if you are a healthcare organization, you have an EMR, and that's you on the bottom of the screen, are probably interested in doing some reporting or analysis out of your EMR. But in many cases, this just isn't possible. The EMR does not support direct querying or direct pulling of data out of its system, at least not with the amount of flexibility you might be looking for. Instead, the EMR, you have a secondary reporting database which you use to report out of. So this is great, but data doesn't get from the EMR to the reporting database by magic. There has to be a process that supports this. And indeed, this is how it works at these organizations. The EMR produces a set of change data. And often this is on a daily cycle. Every day there's a process that figures out everything that's changed in the EMR in the past 24 hours and produces a list of change data files. Those get pushed into the reporting database. The reporting database has all the historical data for as long as you've had your EMR. It takes the new data, it merges it in, and then that data is available for you to report on. Well, the problem is this process is already only running every 24 hours. So the data is already 24 hours in arrears. And additionally, the process of merging itself can be very expensive. So by expense, I mean time consuming. In fact, we've seen with organizations that we work with, a single table being merged on a daily basis taking 2 hours every day. And all the downstream analytics that depends on this reporting database has to wait for those 2 hours in order to do its work. So we read about Delta and Delta Merge, and we thought, this sounds like the perfect tool to help speed up this process. I wonder if we can move this into Delta and get some better results. So that's exactly where we're going to start the demonstration. And I'm going to switch over to the notebook. Okay, so while we in fact did this at a real organization with real data, that real data was rife with private health information and is not appropriate for showing at a conference, virtual or otherwise. So instead, we're going to use this notebook to create some fake data, which is characteristic of the real data that we actually perform this. So we can show exactly how change data capture would be produced by Delta on real data, just using some data that we're going to build on the fly. So that's exactly what I'm going to do here. What this command is doing is we're going to create a table. We're going to create an order table. This is as if this is our historical data. So we're creating a table with 10 million rows. The first column is going to be an order ID column. It's an auto increment column. That's what we use the range function for. And then just for authenticity, we're going to throw in another couple of columns or just a random number, one of 10,000 random numbers that represents a procedure code, and then some fake date that represents the order date. Those are really just there for appearances, just to make the demo feel a little bit more real. After we create that table, we are going to write that out as a delta table. And again, this represents our historical order data. We're repartitioning the table by order ID. That just allows, when we're getting new orders by order ID, which is the primary key, for Delta to sort of select the appropriate partitions that it needs to load up. We have to repartition by range because this is an auto increment key, so it is unique per row. We would have too many partitions. We'd have partition per row if we partition directly on order ID. So this process is completed, and we can take a quick look. So here is our incrementing order ID key, 0 through probably one less than 10 million that we asked for. Randomized procedure codes. These don't actually come into effect, but that's what our order table is. So the next thing we're going to do is create a fake data source that resembles our order update. So this is the daily change data coming out of the EMR in the past 24 hours. Here are all of the orders that have come in new and any edits to existing orders. The way we're building this, we're doing 500,000 rows. The order ID in this case, rather than an incrementing integer, is going to be any of random 20 million integers. So what we expect is that about half of these integers will overlap with the 10 million integers we had in our historical data, and about half will be brand new. So this sort of replicates the idea that we are getting a batch of new orders. Some of them are updates to existing records. Some of them are new. We'll have to merge the old ones and insert the new ones. So once again, we're going to fold in some additional metadata and save that in the same way as a delta table. Now, if we've done our job right, again, the assumption is that we'll get about half the cases where they matched existing IDs and half the case where they didn't, which I'm just using a quick SQL statement joined on our original order table to confirm. And indeed, we see that they're about 50-50 matched versus unmatched. We have slightly fewer than the 500,000 that we requested, and that's because there's no guarantee that these random integers will be unique. So I'm just taking the distinct list of them, and the other ones get tossed away. Okay, so we're good so far, and now we are ready to run our merge operation. And this should be illustrative of how simple Delta makes this. So the merge operation, we're simply going to merge into here's our historical order table, the 10 million rows that we started with. Here is our update data, which is the 250,000 rows that that should overlap, and then roughly 250,000 rows that are inserts. And we match them on order ID. That's our primary key. If that primary key matches, then we are going to update the entirety of the columns for that row to our new merge data. You can specify column by column if you're only updating some of the columns, not the whole set. But in this case, we're going to update all of them. If it does not match, that means we have a new order, and we insert that whole row. So that job is done. If we've done our work correctly, then we should be able to count the rows in this table. And what we'd expect is that we'd keep the 10 million rows that we had before, and all the unmatched rows, the about 247,000, would be added. And indeed, that's what we found. So again, what this is intended to illustrate, and use your imagination. We're using fake data here, but we have demonstrated this at organizations using real data. Is we took a job that their on-premises database has to perform every day, and running up to 2 hours to perform a merge on a single table. In the test that we ran, we were able to get that 2-hour job running in about 10 minutes on a 30-node Databricks cluster, taking advantage of Delta Merge. And the coding for this is super simple, and a lot of the performance just comes out of the underlying system. Okay, so that gets us the data into our system, and now we're ready to prep it. So unfortunately, for our sepsis prediction model, we want modeled sepsis data. And the data coming out of our EMR is typically not going to be, well-modeled data all ready to report, on figures related to sepsis. So we're going to need to do some data prep. Now, it just so happens that Prominence has built a number of sepsis tracking apps before with a number of organizations, and we do a lot of our data prep in SQL. And one of the supported languages on Databricks is SQL through Spark SQL. So what's really nice about this, and this really can't be overstated for organizations who have a lot of their business logic already in SQL and are looking to make the move to the cloud, is that you can take that existing SQL that you've written, potentially thousands, tens of thousands of lines, and often run that with very trivial changes on a Databricks cluster. So here, what we did, again, this job was originally written for their on-premises database, and it ran almost entirely as is with just a copy and paste of the SQL code over to Databricks on Spark SQL. So you can see we're making use of temporary tables, potentially get replaced by temporary views, but we have support for windowed functions. You can see here we have support for common table expressions if you're using those. Again, most of the things that your on-premises database is probably already doing, already supported by Spark SQL. There are a few changes that we had to make. Functions dealing with time had to be, we had to do sort of global find replace on some of those. But again, they were fairly trivial. Copy and paste the thing in, and we get the logic. We ported the logic that we already had for prepping data for sepsis out of the EMR running on Databricks, and in many cases, much, much faster. Another thing you might notice about this notebook is these widgets I've created. So these, what we're doing in this notebook is creating a set of SIRS indicators, which are frequently sort of indicators based on patient vitals and order results, lab results, which can help indicate that the patient, may be getting sepsis. And these are based on certain threshold values. Now, we like to avoid hard coding these threshold values into our scripts for a number of reasons. One is because the number 89 in the middle of a SQL script may not have any context. And while we can sort of prevent or illustrate what we mean by the number 89 through comments, a potentially even better way is give the number 89 a name that actually references what it refers to in the script, and then refer to it by that name in the script. But the other and potentially even more important attribute of these parameters is that if this notebook is run via the Databricks API or via Azure Data Factory on Azure Databricks in an automated way, you can externally set these parameters when you run it by the API. And that means that these values can come from an external system, which is exactly what Prominence does. Whenever we design our ETL scripts, we put these sorts of parameterizations in them so that these values can be pulled out into another system, sort of a data dictionary, where we define precisely what value we're looking for, what it is. It has methods for tracking this value over time. It's when people changing it, add change notes, deploying it between environments, and so forth. And then the values get interjected into the script at runtime. And if you change them sort of in the source system, then they can change throughout all the scripts that refer to them as parameters. So really neat feature. Again, there's an interactive component when you're using it in the notebook, but these really shine when you're using them as an automated process. Anyways, we're not going to run through the details of this notebook, but I do want to point out just at the end result here is that we are going to, using Spark SQL, we pulled the data from the EMR. We've got these raw EMR tables in our Databricks environment. Now we're going to create a table that has the fields that we want to develop our sepsis model off of. And we've done all that in SQL. So, by the way, I'm not sure if I mentioned if you have any questions, I will be answering them after the talk in the chat. So post them there if anything comes up. Okay, so we are ready we have our model table created. We have our data extracted. It's time to jump over to our machine learning notebook and do some model design and data exploration. So again, the concept of unified analytics, the point here is that we can jump between various tasks that are all key and essential in the pipeline of machine learning and analytics in general. We can use it with one system. We can use it often in one interface. So we were just working on one notebook to do our change data capture, a different notebook to do our data prep. And here we are. We're going to jump over to a Python-based notebook and do our model design. And what's great here is that we created this table using Spark SQL, and it kind of felt like we were working with a database, but we want that data now to work as a data frame in our PySpark instance. And it's as easy as here we're pulling our sepsis ml.model table out of our Hive metastore and putting that into a data frame. So we can use the power of notebooks to take a look at what the data looks like. We're going to be doing our machine learning today with random forests. One of the wonderful attributes of random forests is that they don't require as much feature engineering, or at least sort of number manipulation as neural networks and other families of machine learning algorithms, which means we don't have to sort of normalize figures so they're all between 0 and 1. There are a few things we do have to take care of here, though, because our random forest will not take strings. So these gender values need to be dealt with some way. And our random forest will also not deal with nulls. And I happen to know, even though we can't see them here, that some of our length of stays are null. So that's a fairly easy thing to take care of. We use string indexer, which is going to take any of the unique values in gender and just convert them to integers. And we're just going to put that in a new column called gender indexed. And then a little more subtle process for dealing with the nulls. So the column with the nulls is the length of stay column. It's how long the patient was in the hospital. We could just delete the records that are null, but another way we could deal with it is sort of a two-step approach. First, we're going to add an additional column, which is a binary column or a true-false column that says, was the value missing? So when the value of LOS is null, we're going to set it to 1, and otherwise we're going to set it to 0. And so that's the first step, and that way we can use that as an input to our model, and then our model knows whether the length of stay was missing. But additionally, for the original column, anytime we run into the length of stay that is null, we're going to give it the median length of stay of all of our length of stay values, which we've calculated up here, which just kind of puts it in the middle of the road, so it hopefully doesn't affect, it doesn't push the model in one direction or another. So that's the idea here. We can check our work, make sure we've done it correctly. And so here we go, length of stay. We can just, spot quickly and not spotting any nulls, right? And then hopefully here at the far end, yep, gender indexed has been indexed as integers instead of string values. Okay, so the next step is we're going to extract a set of features from our data frame. These are going to be the inputs of the models, what we're going to try to predict off of. This is just a little bit of busy code to get the data ready to feed into our random forest. And here we're just going to split it between training and validation. As a bit of a pedantic note, oftentimes you'd want to split it into three, into training, validation, and then a third set that you're going to set aside for sort of confirmation that through the process of design, if you've gone back and forth between training and validating and modifying your model, you might actually end up overfitting on your validation data, even though you weren't training on it. We won't do that here, but that is something that you should do in your professional machine learning initiatives. So as I mentioned, the random forest is what we're going to be looking at. So what is a random forest? Very quickly, it's a sort of collection of decision trees that that are sort of randomized in some way and come together to vote on a result. So what is a decision tree? It's you've probably, you know what a decision tree is, even if you don't know that you know what a decision tree is. But it's basically what we're looking at here. We have each one of our features is sort of aligned into a tree, and depending on what the value of that feature is, we take one path or another. So in this case, you know, feature 6, whatever that is, if it's greater than 2.5, we're going to go to this, this node of the tree, and if it's less, we go to this. So a random forest is going to create a bunch of randomized trees. It does this by sort of dropping features and then creating another tree, and then dropping different set of features and creating another trees, and then it combines all those trees together into sort of an ensemble result. So the way we do that is very simple using SparkML. We're creating a random forest classifier. We're looking for the sepsis column, which contains whether or not the patient ultimately was septic. And then the featured column we created earlier are all the inputs to that. So we are going to fit our model to the training data. We're going to produce a set of predictions on that, on the validation data. And then I've written a handy little function that will evaluate the success of our model. And we're at 87 now, almost 88%. So we did really well, right? It seems pretty good considering we just went with the defaults. Well, let's take a little bit of a closer look, because if we take a look at our original sepsis data and count how many patients were actually septic, the result is that about 14%. 14 and 86 are not the same number. They're vastly different numbers, and what we have here is called data skew. This is important because with 86% negative results, if we had developed a model that always just said, no, they're not septic, we would still be right 86% of the time. So now our 87.9% accuracy doesn't seem all that great. So there are ways around this. We can't use accuracy whenever we're dealing with skewed results like this. We can use something called precision and recall, and a combination of these two scores called the F1 score. So let's quickly, so I'm going to take advantage of the notebook here. I'm going to actually switch to a SQL-based cell because it's sort of illustrative of how we're going to calculate precision and recall. Precision and recall are based on the concept of false positives and false negatives, which you're probably familiar with. Real clear and easy to represent in SQL. Here, in this case, where sepsis is 0 and our prediction is 1, that's a false positive. Sepsis is 1, prediction is 0, that's a false negative. Sepsis is 1, 1, true positive, true negative. Precision is based on this formula, true positives over true positives plus false negatives. Recall is based on this formula. And then F1, again, often when we're doing model development, we don't want to have to deal with two numbers, especially if we're doing some sort of automated refinement of the models. Just much easier to have a single score, so the F1 score combines these two numbers into one score. So now we have the concept of precision and recall. Again, these are much better measures of success to use if we have data skew, because they both show how often are we right when we're supposed to be right, how often are we wrong or how often are we right when we call it positive, how often are we right when we call it negative. And it turns out our precision is 74 here, recall, and F1 score looks pretty terrible. So clearly we have a bit of work to do. So we're going to go back to our random forest classifier. We went with just the defaults previously. We're going to change a couple of them. We're going to change the depth of the tree. The default is something like 5, so we're going to change it to 20. Deeper trees are more powerful. They can sort of model more complex behavior. They are also more prone to overfitting. However, that is ameliorated a bit by a random forest because of its shuffling of the features in the trees. It does tend to reduce overfitting. There is a computational cost naturally to going with a higher depth. Also, number of trees, we are going to bump that up to 30 trees. Again, there's a computational cost to having more trees, but we'll see if it gets us a better result. Just to get a sense, so we looked at before what a tree of depth of 5 is. So a tree of a depth of 20, the depth of 5 was fairly readable, and we might be able to look at it and make sense of it. When we get to a depth of 20, things are going to be a little bit more sort of less human readable, if you will. So let's give it a second to finish. So this is what a tree of the depth of 20 looks like. So a little less scrutable. Okay, but our updated random forest has run. So we're going to evaluate it again. This time we're going to include precision recall and the F1 score. Again, it took a little bit longer, but we'll see if we get improved results. And fingers crossed, let's see what we get. Okay, so our accuracy is up to about 90% before. Precision is up slightly. Recall is up quite a bit, and our F1 score has increased significantly. There are still a number of, there's still some distance we can go. We can continue to improve this model. There are other parameters we can play with our random forest, including different strategies for how we sort of choose our subset of features every time we randomize the tree. We can play around, continue to play around with the depth and the number of trees, see if we get an improvement or not, or what the computational cost for that improvement is. Another thing we can do is go back to our EMR and see if we can get there are additional features that might lend strength to the model. But we have now a framework for testing the model, testing its performance, and evaluating whether we're improving. Another thing we can do now that we have a model is sort of evaluate how the model works. So not only can we get out of this a way to predict whether a patient will be septic, but we can also take a look at what the model is telling us about how these Sepsis indicators and other sort of features about our patient or the encounter tell us about the chance of that patient getting septic. So the Spark MLlib tree random forest model has feature importances that can report out. The output isn't entirely visually pleasing. Here we have a feature as an integer and then the importance of it. With a little bit of Python, we can fold the actual feature labels back into this feature importances and plot out the results. Let's see what that looks like. And here we go. Now we have a chart, basically what our random forest thinks are the most important features of whether or not a patient will become septic. Total number of SIRS flags that they get is the number 1, followed by age, followed the number of leukocytosis flags, and so on down the list. Another thing we can do is pull out and visualize a single tree. And again, we don't necessarily want to look at we used a max depth of 20, but that's exceedingly difficult to read. But we can still get kind of an overall sense of how the model works at a general level by looking at a smaller tree and just seeing what it's doing. So again, here is the tree with a depth of 5, and we can see our features again and how they're divided. Here we can give ourselves sort of a handy dictionary to interpret this tree. We see feature 6 here, greater than 2.5, it goes to this branch, less than 2.5. Feature 6, we'll check down here, is the number of flags. So that makes sense because here we saw that the most important feature is the number of flags, so it makes sense it would be splitting off on that first. Feature 0, above 16.5, it goes this way, below 16.5, it goes this. Feature 0 is age. Okay, so it's treating them differently if they're age 17 and up versus if they're below 17. Well, that makes sense because people of different ages will have vastly different responses to infection. And again, we get confirmation here that that age was the second most important feature in our random forest. So it makes sense in this sort of one tree that we pulled out that age would be the second. So we can go back down the list and kind of interpret and get an idea of what exactly our model's doing and how it's determining whether or not a patient is septic. So in summary, what we've done, we didn't extract data out of the EMR, but we did look to the EMR to pull change data and see how it merged that into our database more quickly than we were able to do on-prem using Delta Merge. We borrowed SQL logic that we wrote for an on-prem database, just copied and pasted it onto Databricks, and copy replaced some function names and ran it, parameterized it so we can update parameters on the fly. And then we switched over to a Python notebook and began development of our sepsis prediction model. So I hope you enjoyed the data journey today. That is the end of my presentation. A quick request that, hey, if you like what you're doing, if you're interested in working with Prominence or learning more about what we do, please reach out. Our contact information will be available along with the session information. And please provide your feedback on the session. That helps me figure out whether you liked what I did or not. So thank you all, and I will be responding to any questions in the chat box as soon as I can get to them.